Well, I actually survived my first year of grad school. What I was a pain in the ass to deal with. So that means I'm free for the next 4 months, especially since they announced at my school that we won't be starting the fall semester until September, which usually for us it starts around late August. So that's like what 2 weeks of extra summer vacation. That's nice. Just thought I want to throw that out there, just cause. Okay, so in today's video, we're actually going to be proving that the derivative of the natural log of x is equal to 1 over x, but by using the definition of a derivative. So with that, let's get started. So let's recall what the definition of the derivative says. So with the formula, I'm gonna write proof. Let's recall that the derivative of, let's say f of x is equal to ln of x. Well, in this case, let's write f prime of x is equal to the limit as h approaches 0 of f of x plus h minus f of x divided by h. And h being, as h approaches 0 being our error bound, so as it gets closer and closer, then what is its slope at that point in particular. So I'm going to write f of x, say f of x is equal to ln of x. So we can rewrite this as the limit as h approaches 0 of ln of x plus h minus ln of x divided by h. And we can actually rewrite the numerator as just a single logarithm. So using rules of natural logs, we can rewrite this as this. The limit as h approaches 0 of, and this is minus, so using natural log rules, this is actually means divide. So when we're writing this as a single natural log, so the natural log of x plus h divided by x, and then all over h. And when we're also dividing by h, another way we can rewrite this is the multiplicity of its reciprocals. So it's the limit as h approaches 0 of 1 over h, then times the limit, or the natural log of x plus h divided by x. And again, using natural logs as well, 1 over h is being multiplied in front of the natural log. So using the rules, this is actually being moved to as an exponent. So the limit as h approaches 0, and then we can simplify the inside of the natural log, which is just 1, and then plus h divided by x. Or, whoops, I forgot to write the natural log there. Natural log of 1 plus x over h, and that is being raised to 1 over h. Okay, so far so good. So the next step is, this is going to be an interesting one where we're actually going to be using a substitution variable. So let's actually define a substitution variable. We'll call it y. So let y equals, oh wait, actually I have that backwards. This is supposed to be h, this is supposed to be h over x. I accidentally wrote x over h. Sorry about that. There we go, that's better. Yep, okay, h over x. So, as I said, let's actually use a substitution. Let's define y equals h over x. So, one thing to observe is that when we take the limit of the of our h over x, so let's write this h over x. So as we take h approaches 0 of h over x, that's actually equal to 0. But at the same time, that also means that y equals 0, or y approaches 0 technically. So that means this is the same thing as writing the limit as h approaches 0 of y. Or I shouldn't have wrote it like that. This is supposed to be, oopsies. This is supposed to be the same thing as writing the limit as h approaches 0 of y. So, in other words, as h approaches 0, then y approaches 0. So, we can actually rewrite our limits with our substitution. So, the limit as y approaches 0 of let's see the and another thing to another thing to do is, because we're replacing doing a substitution, we also need to fix h. So when you rewrite this is actually the natural log of 1 plus y, since y is equal to h over x, and then h is equal to x times y, so it's just 1 divided by x to the y. And then another fact we need to establish is, or in this case, one thing to note is that we're going to be using Euler's constant, and Euler's constant is defined in terms of limits as e equals the limit as y approaches 0 of 1 plus y divided by 1 over y. I'm not really going to go into detail, but I'm not really going to go into detail with why this is true. Just note that when you're trying to prove the natural log using the definition of a derivative, this is an important key to use as we proceed forward. So we're going to be using that. E is equal to the limit as y approaches 0 of 1 plus y raised to 1 over y. So when we do that, now going back to here, we can actually 1 over x is actually considered the constant, because we are also taking the variable as y approaches 0. So what we can do is we can actually factor out the 1 over x from the exponent on the top, and then actually using natural log rules again and move the 1 over x to in front of the natural log. So an arrow there. So in other words, this is written as the limit as y approaches 0 of 1 over x, the natural log of 1 plus y, 1 over y, and then 1 over y being distributed is used as the root. So it's the same thing as saying the y root of 1 plus y. If you want to be technical, I can write it this way: 1 over x of the natural log of the y root of 1 plus y, and then this is actually equal to e, so 1 over x times ln of e being equal to 1, so it's just 1 over x. And for the sake of it, let's actually let's have some fun. Why don't we actually prove that the natural log of x equals 1 over x by using implicit differentiation. So let's let y equals, I think I got room to put this here, right? Yes, I do. Okay, so let y, let's actually use a different, use black for this instead. And I got that, don't worry about it. Let's define y equals the natural log of x. I'm gonna need my chair for this since I'm gonna have to bend down. So let y equals x. So we can actually take the e raised to this, since the inverse of natural log of x is e to the x. So we do this. Oops, it's e to the y equals e to the natural log of x. Okay, so e to the natural log of x is actually just equal to x, and so it's just e to the y equals x. So now we can actually apply implicit differentiation. So the derivative of e to the y is, in respect to y, is e to the y, but we're also taking it in respect to x, so you have to multiply the dy dx, rules of implicit differentiation, and then the derivative of x is just 1. And dy dx is the Leibniz notation for the derivative of f prime of x, it's the same thing. So we can actually divide e to the y to both sides, so it's just dy dx equals 1 over e to the y. And then we have that e to the y is equal to x substituted for that. Then we have dy dx, also known as f prime of x, but since this is implicit differentiation, you use dy dx, but I'm just use as f prime of x since it's the same, which is also equal to 1 over x, like so. And there you have it. I don't remember when I took this when I took like introductory calculus in high school. I don't think I was given we were given the rundown or the proof of why the natural log of x is equal to 1 over x. I remember learning proving trig functions using definitions of definition of the derivative, but I don't think natural log we learn anything using natural log. Especially, I don't even think they will teach you this proof in whenever you're taking an introduction calculus course, even in college, especially, because I don't think that's what happened to me when I first stepped in. But if you're curious, the entire proof is like this, like so. There you have it. If you're ever curious, this is a step to do it. So, pretty short video, I know, but you know, I gotta make something. So, thank you guys for watching. If you're new to the channel, like, comment, and subscribe. I did a proof of Euler's formula, e to the I theta equals cosine theta plus I times sine theta. It's a very interesting proof, especially to every single mathematician, and I think it's worth checking out. So yeah, I'm done with school. Don't worry about that. I wonder what my Animal Crossing village is like. Maybe I should probably check that out.